I will start with the outline of my presentation. I will talk about the motivation of this work. Then I will talk about the new fiber reinforced concrete made with recycled steel fibers. I will show some flexural tests on this type of FRC, and then I will perform a so-called eco-mechanical analysis in order to select the best concrete, the best FRC among a series of FRC, which has the best mechanical and environmental performances. So, of course, the goal is to increase the sustainability of cement-based materials. And a way to reach this target is to substitute part of the components, or yes, the part of the component of concrete with waste. For instance, steel from end-of-life tires or plastic waste, which cannot be recycled. And here you have the steel fibers and plastic materials that we used for casting the new FRC. By using these materials, we have a double benefit, because we reduce the depletion of natural resources, and of course we reduce the landfill disposal as well. However, another possibility of increasing the sustainability of concrete or cement-based materials is to increase the performances. And in particular, in the case of FRC, if we increase the content of fibers, we can increase the performance, not only in terms of toughness, but also in terms of strength. Here you have some results. One of the first results given by Bagot in 1983 from uniaxial tensile test on different FRC. In particular, he changed the length of the fiber with the same diameter, and with a single length, he used a different percentage in volume of fiber. As you can see, by increasing the percentage of fibers, you increase the strength as well. In particular, when you have long fibers, by using 5% in volume, you reach a strength which is about twice the value that you have in when 2.5% in volume of steel fibers is used. So we doubled the content of fibers, but the strength as well. But the cost, the environmental impact is not doubled. So this is particularly convenient because we can reduce the mass of total concrete and the mass of carbon footprint of our materials. However, the cost from 2.5% in volume to 5% in volume of FRC increased, and so if we want to maintain the performance strategy, if we want to apply the performance strategy and also the substitution strategy, we can use recycled steel fibers because they are cheaper than the manufactured steel fibers, industrially manufactured, of course. The problem of these fibers, however, is the balling phenomenon that you have, and as it is not so easy to separate and distribute uniformly the fibers in the concrete mass, our idea was to use directly this ball or growing or this mass of steel as you receive it from the shredder. So you can put it directly in the mold, and then you had a grout or a slurry directly on this on this amount of fiber. In other words, we can apply the strategies of performance and substitution by using recycled steel fibers and a two-stage procedure for casting the concrete. In the first stage, we put the steel fibers, a large volume of these fibers in the mold, and in the second stage, we injecting the grout. With this idea, we in practice cast two series of FRC. This series was made with the goal of improving the environmental and mechanical performances of our reference cement-based matrix. This matrix was, or this FRC was composed by water, cement, 52.5, type 1, and then sand, the traditional sand that we use for testing the cement. Then, in this case, we used 2.1% in volume of steel fibers, and of course, super plasticizer. This reference composite is made with one-stage casting procedure. With respect to this, we, in the series 1, we increased the amount of water and the cement as well, but to maintain the same water binder ratio, we added silica fume. Then, instead of the traditional sand, we used a modified sand in which we eliminated the plastic, the grains, the particles, which has a size of larger than 200 microns. So only particles lower than 200 microns were used as in this modified sand. And we used also plastic waste in grains, of course, of size lower than 200 microns. So we cast three series, different, for series 1, 3 different composite by changing the volume of recycled steel fibers. The same we did also for test number 2. We used the same content of water, but we used the same content of cement of reference. So we didn't increase the cement, but to maintain the water binder ratio, we added a larger quantity of silica fume. In this case, we used only modified sand without plastic waste. These are the series of FRC we used, and here you have in particular the properties of recycled steel fibers. Obviously, you don't have the same diameter, the same length of these fibers. And here you have the distribution regarding the diameter and the length of the fiber. and the average value are reported here. We also computed for these fibers the aspect ratio, which is 62.8, and in the reference composite, we used a manufactured steel fiber which has more or less the same aspect ratio. So, according to the standards for testing cements, we cast 3 samples for each composite, and with these specimens, we can perform both flexural and compressive tests. In particular, the first test is the bending test. After this bending test, we have a break in the specimen, and both the halves of the specimen can be tested in compression. So I just comment some results, in particular from the flexural test, we obtained the flexural strength. And both in the case of series 1 and series 2, the strength, the flexural strength, increases linearly with the content of fibers. As you can see, these square are the test results. Then you have the trend line here, and in these circles are the results of series number 2, and of course this is the linear trend that we have. And with respect to the reference composite, which has a strength equal to more or less 10 megapascal, we can reach the same strength with the series 1 when the content of fiber is more or less 4.1 here. And on the contrary, in the reference, in the series 2, we can reach the same strength of reference system when the content of fiber is 3.1. So in practice, we can have three composite with the same properties or the same strength. The reference, series 1 with 4.1% of fibers, recycled steel fibers, and series 2 with 3.1% of recycled steel fibers. So the question is, which of these 3 composites is the most sustainable, is the best solution that we can have, not only from a mechanical point of view, but also from an environmental point of view. For this reason, we performed the eco-mechanical analysis. In particular, we consider 2 parameters, MI, mechanical index, and EI, the ecological index. MI is the so-called functional unit. So in practice, the performances, the mechanical performance that we want from our composite. In this case, we just consider the flexural strength. Anyway, other mechanical properties can be introduced here. Then we have EI as the environmental impact, which can be, for instance, the carbon footprint on materials. Of course, we have 2 limits for MI and EI. In practice, the minimum value of MI, the mechanical performances that we want, and the maximum impact, so the maximum value of EI. And here we consider them as those of the reference composite. So in this diagram, if we use on the ordinate the ratio between the maximum impact and the impact, and on the abscissa the mechanical mechanical index and the minimum value of this mechanical index, in the one point we have the reference system, and in this sector number 3 in this picture, we have the best performances with the low environmental impact and high mechanical performances. So our goal is to find a new composite which is here with respect to the reference system 1. So as we tested in bending and calculated F, the flexural strength, our goal now is to evaluate EI. EI can be computed by considering the carbon footprint of the material component, of the concrete components. And here you have some of them and database from which we obtained this information. It is really important to see that the impact of recycled steel fibers can be considered about 0, especially with respect to the impact of industrial steel fibers and cement as well. So the EI is the product, or is the sum of the product of these values of carbon footprint related to mass of concrete times the mass of material that we are going to use in the composite. Here you have the results for the specimens we considered in our analysis. Obviously, the largest impact is that of reference system, because we are using Portland cement and industrial steel fibers. On the contrary, the lowest impact is that of series 2, because we reduced the cement with respect to reference 1, although the content of fibers is that of recycled steel fibers, so with 0 impact. So these are the... Okay, thank you. And this is the results of our eco-mechanical analysis. As you can see, here we have the reference 1, 1, and then these square these squares are the results of series 1. As you can see, we reduced the impact of the reference system, but to reach the sector 3, this one, where we have the best ecological and mechanical solution, we need in this series 1 at least 4.1% in volume of steel fibers. Then here you have the results of series 2, where you are in field 3 when the content of recycled steel fiber is larger than 3.1. So, in other words, if we properly define the content of recycled steel fibers, we can create with the two-stage procedure new fiber-reinforced composites, which can be more sustainable than those made with only virgin materials. So these are the conclusion. We created with a two-stage procedure new cement-based composites made with a large volume of recycling steel fibers. By doing this and by tailoring the materials, we can obtain both the best performances, both intention, so both from a mechanical point of view, and also related to the carbon footprint, so the environmental impact. And thank you very much for your attention.